So thank you again. So my head and my throat are not in top shape, so I will talk as long as my voice allows, and if my voice goes out, then we just stop, I guess. Thanks to Laurent for the problem here. Okay, so yeah, I hope no one has any super technical questions that require long calculations, because I'm in bad shape and Vlad is not here. So I'll try to summarize what sort of the end of the proof that Vlad was explaining. So let's see, what did we have? We had a construction of a sort of multi-scale vector field. I don't remember what Vlad called the vector field, but I will call it B. Okay, and so you remember that this B was somehow okay, so it was first the grad perp of some psi. So what we really did is we built these stream matrices of our vector field. And the psi was some sum. Actually, he called it phi, didn't he? Well, anyway. The psi was, let me call it phi. Phi was the limit as m goes to infinity of phi m, where phi m was the sort of approximation of our field, or of the stream matrix, having scales epsilon 0, epsilon 1, ... epsilon m. So the problem with this construction is there's, of course, way too many parameters, and I can't remember them all, and so probably you can't either. But one of the main things to remember is that we have just a sequence of length scales, and so these things are these are not, so I think 1 is equal to this one, and then we go down the scales like this. Okay, and the gap between two scales is a little bit wider than geometric. Okay, so that you can think of, so more physical would be if the gap was geometric, and that would mean that epsilon m plus 1 would be some small constant times epsilon m. Okay, but we can't quite do that. It's not convenient for our, we need the proof to work at the end of the day too. So we just make this constant epsilon m to a very small power. So we make this one be epsilon m to a very small power, which we wrote as q minus 1 for some parameter that's yet another parameter, and then we can erase this like that. Okay, so you can think of this as just being slightly more than geometric, so the gap between any two scales is a power of the scale you're at, but a very small power. Okay? All right, so this sort of super geometric separation will makes the proof easier. And the reason it makes the proof easier is because it says that really when you're analyzing the problem, you only have interaction between two scales. Because if you have geometrically separated scales, and you're, scale 1, scale 1 over 10, scale 1 over 100, and so on, then two scales will clearly interact. But also, the ones that are apart by, m and m plus 2 will also interact a little bit, and you'll have kind of a lot of interactions that you have to keep track of. And so we don't want to do that. Okay, so this makes the proof easier because only two scales will interact. Okay, and I can explain where in the proof that this comes. Okay. All right, now associated with the length scales, there were also time scales, right? There were these taus, and the taus are kind of adapted more or less to the epsilons, so there were also time scales. And these are also getting smaller. Okay, and these taus are roughly, they're not quite exactly this, but roughly speaking, tau m should be kappa m. So let's see, so diffusivity is length squared over time. Yeah, so I should put epsilon m squared, roughly. Okay? This will be off by a very small power of epsilon proportional to q minus 1, but this is what you should think. Okay? So that these time scales are really associated to these length scales. So the vector field has these scales and it has these scales. Okay? And you remember that what we're essentially trying to do is to make the spatial scales, the wiggles at every scale are just very simple shears that alternate in time between horizontal shears and vertical shears. And we like to make it a very simple shear flow because we can analyze that. We can analyze the effect of one scale of shear flow very, very well. Okay, because it has an exact formula, we know what happens, it's very nice. And so we're just trying to set up the problem in such a way that whenever we look at one scale and see what it's doing, it reduces to that sort of very simple shear flow, which is almost a 1D situation. Okay? And the whole complexity of the construction is to really make that picture, that little incremental step be simple. And in order to make that simple, we have to make the vector field complicated. Okay? So I won't write down the full formula, but remember that the time dependence, this has time dependence because, and really only because, we need to wire in the sweeping of smaller scales by larger scales. Okay, so we need that. So in order that when we're looking at scale, I don't know, epsilon m, and we are looking at the effect of what's happening on that scale, we need all the other sort of larger scales to not mess it up. And in order for them to not mess it up, we need to have this scale's wiggles be kind of advected by the flow of all the other guys. So that's why when Vlad wrote down the formula, he composed with the inverse flow map. And what that does is it kind of says, if you change coordinates into Lagrangian coordinates, then when you look at what's happening at this scale, it's kind of stationary and nothing is moving, kind of at leading order. Okay? And so that was the point. So this is the only reason that the vector field picks up time dependence. But then, of course, the time dependence becomes quite complicated because you can imagine at the first scale, you put in some shear flow wiggles, okay, and you look at the Lagrangian trajectories of those. They're quite simple because the shear flow just goes in a straight line, so the Lagrangian trajectories go in a straight line. Okay, so you can figure that out. But then when you put in the second set of shears, you have to compose with that flow. And so those shears, which are on a smaller scale, get kind of deformed a bit. And then when you go to compute the Lagrangian flow map of that, now it's kind of getting messy, because then the trajectories are doing weird stuff. But then when you put in the next scale, you have to compose with that, and it gets really it becomes a big mess, okay? And it's not even easy to simulate, at least for us. There's people here that know how to do it. We tried to simulate, Vlad and I, we were asking ChatGPT to help us write the code because we're not such, code writing aficionados. So we could compute the Lagrangian flow map for the third one, I think. But after that, our code wouldn't compile. And when it did compile, the picture looked terrible and was wrong. So it's almost, the example is almost built in such a way that it makes it as hard as possible to compute the Lagrangian flow map, even numerically. Okay, so, yeah. So we were impressed when we finally saw the pictures. Anyway, so this is the picture of the vector field. It's constructed in such a way to make the analysis easy, right? So we are not starting with a real physical vector field and saying, okay, we want to understand what happens. We're working backwards. We have we do the sort of mathematician's vice of saying, I have a proof that I want to make work. Let me change the assumptions until the proof works. Okay? Which is, yeah. Yeah. So, okay, so how does this proof work now? we have a family of equations, one at every cutoff scale. Okay, so you can look at each one of these. You can let the Bm be the grad perp of this guy. Okay, and this is going to be the vector field with all the scales below this one just not appearing there. It's just completely cut off. Okay, so we have a family of these equations like this. What am I doing? I should write the time derivative as well here. So we're going to index them by m, not kappa m now. Okay. So here's our passive scalar. And these are all given the same initial data. Okay, so I'm going to solve this on all of time across the torus and give it initial data. And the way that the proof works is we sort of argue that all of this whole family of equations are all the same in some sense. All of the theta m's are the same. And then we say, well, now so the proof says all of these solutions to the different equations are the same, up to some error that's acceptable. Okay, up to an acceptable error. Okay, now the error gets larger for the smaller m, right? So as you go to the larger scale, the coarse graining creates a larger error. The thing is actually working better for the smaller scales. And that's because of this sort of supergeometric scale separation. Okay? And then the way that we conclude, as Vlad explained in the last lecture, is we say, well, now suppose that you're given a kappa, a small parameter kappa, and you're given the full vector field B, which is not Bm. Okay? If your kappa happens to lie along this sequence of kappas that we defined recursively, then I can kind of identify the real equation with one of these for that particular kappa m. And then, okay, I have Bm here, not B, but actually those are, the only difference there are really small scales that are smaller than this diffusivity, and so we can get rid of them with an easy sort of comparison. You know, the difference between Bm and B will be erased by the diffusion, okay, because that difference is on such a small scale that the molecular diffusivity kills it, okay? And so the main part of the proof is just to show this, that all these equations are the same. Okay, and you can recognize this as a homogenization statement. Okay, so this is a homogenization statement. Okay, so let me give a little bit of context to this. What homogenization is, for those who don't know, and how this is actually it actually is just a homogenization statement. And one way to, let me give some historical remarks because I think they're funny. So if you look in Frisch's book called Turbulence, I think the book is called Turbulence. The legacy of Komogorov or something like this. Okay, so Frisch's book on turbulence, I really like this book, by the way. I don't know if you like it, but I learned a lot, because when we started this project, I had no idea about turbulence or what it meant or anything like that. So I learned everything from this book. So I have all my intuition from this. And if you look in the very, very last chapter, I think it's chapter 9.6. Okay, so in chapter 9 is like a chapter of speculations. You know, it's like further reading, a guided tour to further topics. Okay, and Section 6 is far out in the further topics, and he wants to talk about multi-scale methods and renormalization group. Okay, and so what he basically says is, it would be, unfortunately, there's no real way to rigorously analyze these turbulence models. And then he explains, well, there is some rigorous work, and you can use something called homogenization to do it. So he explains, so he talks about homogenization, and he says, And what is homogenization? Homogenization is a way of rigorously kind of integrating out small-scale wiggles and getting an effective equation without those wiggles. That is in the sort of math community. And he says, it's nice that they can do these rigorous results. Unfortunately, this will never be more than a pedagogical device because you can never make it work for what we really want, because in these homogenization results, they have to assume kind of a limit of infinite scale separation. They need the coefficients to be periodic, which is kind of an idealization and not really real. And if you want to really do, understand turbulence, you need to sort of, as he calls it, make an admixture of these multi-scale homogenization methods with more heuristic elements like renormalization group. So he says renormalization group is better because while being just heuristic, we're physicists, I guess, and we don't care, because anyway, this is going to be rather limited. And I think that that's a fairly fair summary of the situation. What I've done in my research life for the last 10 years, though, is to really try to understand the homogenization limit, this way of zooming out on an equation and replacing it with an effective equation. My collaborators and I have been trying to understand that in a quantitative way and with random fields. And the methods that we have kind of come up with are rather close to renormalization group arguments, actually. And now we see our sort of approach to homogenization as a way of formalizing renormalization group methods. And we cannot handle the really, really physical turbulent fields yet, because that's really hard, but we can kind of begin to handle some fields which are Gaussian fields and are starting to look a little bit like, at least they're noisy and they have many scales, okay? However, in this work with Vlad, it's not really in that direction, because we just wanted to make an example for which there is some sort of homogenization argument that is able to make sense of many, many, many interacting scales. Because in 1995, when Frisch was writing, the homogenization proofs are really restricted to the case, it's like the limits are soft and you're taking the limit of infinite scale separation. And just to put a finer point on it, I mean, here I have an equation Bm, and I want to compare the equation for Bm to the equation for Bm minus 1. And then I want to kind of, telescope the error across all of those comparisons so that I know that all of the equations are the same. And so when you're comparing Bm to Bm minus 1, you need that the homogenization, as it were, happens between epsilon m and epsilon m minus 1. So you kind of have a finite budget of gap between the scales. You can't make this gap go to infinity and argue in some soft limit, okay? But we're able to do that because, well, basically because we've designed our vector field so that it's simple. And so we've designed our vector field in order that the proof can work. And so let me give a kind of rough idea of how you prove this without writing all the details, because the essence of what's going on, the idea is rather simple, and the proof itself is quite complicated. There's a lot of calculations, and the main reason for that is because of this. Because when we have to compose with the Lagrangian flows, it makes a gigantic mess. And the Lagrangian flows cause all kinds of weird distortions at next order. And we have to actually analyze those next order errors in order to close our proof. And that involves many calculations. But so let me try to just give a heuristic for how the proof works. And I will not give all the details, okay? So how does homogenization work? Okay, so this equation, we actually don't think about the vector field very much. We think about these stream matrices. So we can, like we said yesterday, we can write this entire part here as divergence of some matrix AM grad. And the AM is actually kappa m, and then it's plus phi m here. and minus phi m here. Okay, so the matrix has constants on the diagonal, kappa m, and then it has this stream matrix on the off diagonal, and this matrix has many scales. Okay. So now let me kind of abstract this a bit to the case in which the matrix has only 2 scales. So now we're going to consider a matrix A of y, which is periodic. Say ZD periodic. And we want to look at this equation. So I'm going to take out time and just look at the time-independent equation because it's simpler. And the time dependence here is really macroscopic in a sense. There's no weird parameters on the time derivative, nor is there any oscillating coefficient. So there's not really much difference between analyzing the time-dependent equation and the time-independent equation. So I'm going to analyze the time-independent equation. And I'm going to put a small parameter epsilon there in the matrix. So this epsilon you can think of as epsilon m or something. And I want to look at this problem. Okay, and in order to make this not be 0, maybe I have to give it a boundary condition or something. You can also put a function on the right-hand side, but let me give it a boundary condition. Okay, so this would be in some, nice, let's say in the unit ball. Okay. All right, so this is not so much different from what I have. The thing I have up here has many scales. But actually what we're going to do is we're going to really think of it like this, and we're going to only have 1 scale because we're going to be doing our homogenization in between scale epsilon m and epsilon m minus 1. And so we're going to kind of freeze all those other macroscopic variables. We're going to kind of hold them fixed. Now the need to hold them fixed actually causes 50 pages of estimates that you have to do, but let's just not worry about that. So we can really reduce to the case where we have kind of one thing like this. And so I want to show you how this problem is actually quite easy to analyze, okay? So the way that this is done is we're going to first define what the effective matrix is. And this is related to what I wrote down yesterday. And then we're going to look at the macroscopic equation, which has that effective matrix replacing this. And then we're going to show that the solutions are close, okay? And I'm going to sketch the proof. Again, the calculation is 5 lines, but that may be like 3 more lines than I can do in my current state. So I'll just kind of sketch the proof. So first we need to introduce the effective matrix. And this is where, if you're following up here, this is where we're going to use the sequence of kappas that we defined. Remember, it has a recurrence relation, and the recurrence relation is chosen exactly so that when you make the effective matrix, it agrees with the kappa m minus 1 equation, okay? So we're going to introduce the effective or homogenized matrix. And so what we do is we're going to let EI dot A bar EJ be by definition the integral over 1 period of EI plus grad, now I'm using phi, I should use a different letter now, chi, EI dot A of y EJ plus grad chi EJ. So there's no epsilon in this definition, of course. It should be epsilon free. And I define it like this, where you remember that these guys are, this whole thing in parentheses here is the gradient of the corrected affine function. So we want that minus the divergence of A of x, I guess, EI plus the gradient chi EI be 0. Okay, so we consider x mapping to EI dot x plus chi EI of x to be the corrected affine. The corrected affine function solution. Okay, so what do I mean? I mean that one thing that you'll notice about this equation is if you plug in an affine function so that the gradient is constant, it's not a solution unless the rows of A happen to be divergence free, but you don't assume that that's true in general, and it won't be true in our case. So affine functions are not solutions, but what you'd like to do is to kind of, we believe that there should be a solution that's kind of tracking an affine, because an affine function is a solution of the limiting equation. So we pick a slope E, and we look for a solution of the equation, which is kind of making periodic wiggles around that affine function. And we call this one, we don't call this chi. Chi is the difference between the affine function and the corrected affine. So chi is like the wiggles you have to add to the affine so that you get a solution. Okay? So it's, and this one should be periodic. Okay? You don't have to make it periodic. You can define these correctors in like a large box or something like that. But this is a convenient thing to do because now you can take the average of the energy of these correctors to define your A bar. Okay? So this is the A bar here. That gives you a matrix. Okay? So now we're going to look at, step 2 is look at the effective equation. Okay, the effective equation should be minus divergence A bar grad, let me call it U bar, equals 0. This is what we think should happen. Okay. Why do we think that this should be the solution? Well, the proof that this is the right thing is quite simple, so let me just sketch it. Okay, so in order to compare the U bar to the U epsilon, we're going to make a guess for what U epsilon should look like in terms of U bar, and then we're going to check that that guess is correct. Okay, so 3 2-scale ansatz. So I should say in the homogenization sort of community, there's all kinds of abstract, complicated proofs for this convergence. And but in this particular case, when we have a periodic matrix, I should say that the matrix is uniformly elliptic. So the matrix is going to have this property. So it's going to be bounded below in that sense. We need the matrix to not necessarily be symmetric, so I also need that it's bounded above like that. Okay, so this is sort of uniform ellipticity. Right, for my example, I don't have a symmetric matrix, so I need that it have a skew symmetric part. But if you have a uniformly elliptic matrix and you're set up like this, then there's a really simple proof, and the Russians like this proof better. And in the Russian school of homogenization, they write this proof. And it's called guess the solution and check that the guess is correct. So what you do is you say, well, what should the solution here look like if we believe that it's approximated by this equation? So we look at the solution U bar. And because this A bar is now a constant, this is really just an anisotropic Laplace equation. So the solutions are completely smooth in C infinity. So let me just, I know that in 1D they're all straight lines, but let me just imagine that this is the solution U bar. Okay, then on kind of intermediate or mesoscales, this U bar, because it's essentially harmonic, should be close to an affine function, by Taylor's formula or whatever. So on small scales, it can be approximated by affines. Okay? And so in order to make what the U epsilon should look like, we know how to correct affines by adding wiggles. And so what we should do is we should just kind of add local wiggles with the correct, depending on the local slope given by the U bar. And these wiggles are kind of linear in that slope. So if we add the correct wiggles, that should give the solution. And because now we have the matrix scaled down by epsilon, the wiggles should be squished by epsilon, but also vertically squished, so that when we take their gradient, we get something of order 1. Okay? And so anyway, I want to take this picture, kind of blow it up. I see a straight line for U bar, and I say, well, what can U epsilon look like? It's got to look like exactly that there. And then I'm going to take this and put it back there. Okay? Now, the wiggles depend on the local slope, and the local slope is changing, but it's changing on the macroscopic scale, so very slowly. And so the distortion caused by that will cause an error, but that error should be next order in the parameter epsilon here. And so that's what happens. So we make this guess called the two-scale expansion or whatever. It's going to be, first we're going to say it's going to look like U, and then it's going to have the correct wiggles attached. The wiggles, instead of having slope E, should have slope grad U. So we should write partial xj of U bar of x, and then we should put the correct corrector here, chi ej. And we should put x over epsilon for the scale. And then we should put epsilon, because like I said, we should squish the wiggles, but also squish them vertically. So this is the guess. You guess that the wiggles should be sort of like this. They should be height epsilon and frequency or wavelength epsilon. Okay, and so then we're going to plug this into the equation, plug this W epsilon into the equation for U epsilon. Okay, now the fact that that U bar has the same boundary data as U epsilon, and the fact that my periodic correctors are at most perturbing the boundary condition by epsilon means that I essentially have the same boundary data for this W as I do for the U epsilon, so I'll make an error of order epsilon in the boundary condition. And when I plug this in here, because of the corrector equation, I have almost a solution. Okay, and so what we find is that when we plug this into the equation, we get an error. The error can be put into divergence form. Okay, and the error is of order epsilon. And the prefactor constants in the error, it's order epsilon times something about U bar, and it should be something about the second derivatives of U bar. Okay, because the second derivatives of U bar tell you how quickly the first derivatives can locally change, and that's the error that you should see. In order to do this, you have to critically use that you've defined A bar correctly. And the fact that you've defined A bar correctly, when you do the calculation, will show up, because you will find the difference between a quantity like this, or actually the flux, and the A bar. And you'll know that because you've defined A bar correctly, that you're going to have a periodic function here showing up, but it'll be centered. Its mean will be 0, and that will allow you to write it like this. Okay, so so I've got this one, and then what I can do is I can say, well, this is also equal to f plus order epsilon. Okay, so this W epsilon that I constructed as a guess for this is close in both things here, and so it should be close to U epsilon. So then you can get that U epsilon minus W epsilon is small in H1. Okay? And now that you know that U epsilon minus W epsilon is small in H1, so its gradients are also close, you can look at this and say, well, this thing is also an order epsilon perturbation, not in the gradient, but in the function itself. And so this will imply that U epsilon minus U bar in L2, not in H1, because they won't be close in H1, but in L2, they're also order epsilon. Okay, so that's sort of how the analysis works. It's very, you can compute everything. So this is classical and was known in 1975. or whatever, but I just wanted to give an overview. Our proof that the theta m equation and the theta m minus 1 equation are close to each other is based on the same calculation. Okay, so the proof that, I'll just say theta m and theta m minus 1 are close, is based on the same calculation. Okay, it's just that in the case of periodic homogenization, the calculation is 1 page, and in the case that we do, it's many, it's 50 pages or something, and that's not because it's just because that there's more error terms, but those error terms are all small. So the idea is really just that. It's just that to prove it works, it's just you have to do a lot of calculations. Okay, are there any questions at this point? Is good? It's pedagogic.
Yes.
Okay.
You said that you needed infinite separation of scales.
Yeah. So here. Okay. Yeah. So that's a good point. So here it looks like everything is quantitative. So you can make epsilon really small and you get a small number, and that's right. So here everything can be quantified. Yeah. And this big O, what do the constants in the big O depend on? Well, it depends on the smoothness of the U-bar here. So that kind of comes down to what is the smoothness of the F, if you want. And in our problem, it depends on the smoothness of the initial data. Okay? But there are other constants in here, and those constants are really having to do with these numbers, the uniform ellipticity constants. And so they depend on this parameter, the ratio, which we call the ellipticity, or the ellipticity contrast. Okay? And in the case of periodic homogenization, because I can solve this easily, and okay, I can estimate everything, getting the correct estimate here, as it depends on the ellipticity contrast, is quite easy. Okay? So I should say the big O of epsilon hides dependence on the ellipticity constant, or the ellipticity contrast. Which, in the case of periodic coefficients, because A of x is periodic, is rather explicit. Okay, and so we can figure out exactly how far the epsilon has to be, the gap between 1 and epsilon. So I guess just how small epsilon has to be, depending on this number. Now, in our case, one of the difficulties in the proof with Vlad exactly is that our ellipticity contrast is blowing up. The ellipticity contrast between two scales was this, if you remember from his lecture, he had this parameter am epsilon m squared over kappa m. Okay, so he had what he called a dimensionless parameter. Okay, and the dimensionless parameter that he wrote here was exactly the ellipticity contrast if you write it like this. Okay, and so this is what happens in our situation, and this number is very, very big. I mean, it's not so big, but it's blowing up. So I think in our case, this number is exactly that parameter gamma. Okay, so it's epsilon m to the minus gamma, and so this is blowing up. Okay, so this is actually maybe the main technical constraint in our work. So I wanted to say, why are we using all these periodic shear ingredients so much? Can we take our construction and make the fields random to maybe have a more convincing example? And the answer is no, because our ellipticity contrast is blowing up, and that causes major problems, so that when you try to carry out this homogenization in the random case, you have big, big, big problems, and the constants are not explicit, and it's open. We don't know how to do it. Okay, so that's actually the main constraint in making our methods work on more general things. In fact, I was speaking about how in most of my research, I'm actually interested in homogenization, but not in the periodic case. I'm interested in the random case. And a lot of my work with my collaborators is to exactly figure out how we can quantify the scale that you need to zoom out at to see homogenization happen. And if we could ever quantify that, if we could do better than we currently know how to do, then we could return to and make sort of random versions of these examples and actually maybe analyze more generic vector fields. Okay? All right. So, any other comments, questions?
So the norm of the gradient square of u in each level, it will be somehow fixed.
That number?
Yeah.
So it's kind of technical what you can put here. I mean, you don't, if f is not, so if f is smooth and you're in the ball, then this will just be some number. If f is a bit rough, then you will be smooth kind of away from the boundary, so then you'll have to cut a boundary layer out where you have a less good estimate, but it's in a set of small measure, and you'll have, so you have some technical things to do. But the same ideas still work. Yeah. So yeah, there's a lot of annoying, complicated analysis arguments that you could get into, and when you do the proof, you have to get into, but they are also distracting from the philosophy of the proof. Okay. In our case, so in our case, we have a particular technical issue because when we go to show that the theta m and theta m minus 1 solutions are close, we have a problem because the theta m minus 1 solution, when you prove the regularity estimates that you need, because you need some higher derivative estimates on the theta m minus, because when we do the expansion like this, okay, in our case, we're going to have something here, which is going to approximate the theta m solution. And here we're going to put theta m minus 1, theta m minus 1. So theta m minus 1 is the macroscopic function for theta m in the sort of ansatz. We actually have a very complicated ansatz, because then there's all kinds of next order terms that we have to include in our ansatz to make the proof work, and it's a giant mess. But we have trouble bounding this because our theta m minus 1 solution is not such a great, it's not so smooth. All the smoothness comes from this, which when m is large is actually kind of small and not giving you much regularity. So what do you do? Well, a couple things. One is that our entire argument is focused on small scales. So on small scales, this thing is not so bad. However, the estimate that we use is probably not a sharp estimate, and everywhere else in the proof we have to be super sharp. But when we get the higher derivative estimates on theta m minus 1, we can get away with a not so sharp estimate because we have a little bit of leeway. And that has to do with the fact that, as Vlad was explaining, when we have this restriction alpha less than a third, remember that we had all these parameters, and in order to make the argument work, we had to show that we can actually choose them in a consistent way. And you can do that if and only if alpha is less than a third, and alpha is the regularity of this vector field, right? And this alpha less than 1/3 restriction really comes from something about the time scales, not from the length scales. You need that the time, and so the time scales are causing this. If it was just about the length scales, we would have alpha less than 1. And because we have this little bit of gap when it comes to the length scales, we can get away with a kind of suboptimal estimate on the second derivatives or whatever of the theta m minus 1 when we do the proof. And the fact that we noticed this sort of technical thing is what allowed the paper to be finished, because we were trying to make the optimal estimate, and it would have been like 300 pages or something. And then finally we noticed that we could make a kind of suboptimal estimate and close the argument, and so we finished the paper. But in any case, it becomes very technical, but this is the main idea. So the other thing that I wanted to talk about, and let's see, so I still have, yeah?
A question about this sort of
Yeah.
strategy. You clearly have to make many, many decisions as you pursued this for a long time.
Yeah.
And you imagine a lot of the attitude has to be sort of not to take no for an answer and keep on pushing.
Yes.
But you singled out and blocked it as well that alpha less than a third is
not something done for convenience. It really is a hard stop. How do you decide that that's something you can't, like what was the other bit you kind of got around with, but you were both very clear that this is not something where this thing can go.
Okay, so why do we believe so strongly that this is actually a real constraint here? Okay, because, yeah, so how can I explain that? In order to make so we're making an example. So there are other examples of the diffusive anomaly. In those examples, I mean, you have to have a cascade of link scales. Like you have to have communication between all the scales. And the way that the other papers make the communication between the scales is that they have the scales that are turned on are separated in time. First you turn on the low mode, and then in the next time interval you turn on a higher mode, and then you turn on the higher mode, turn on the higher mode. But at any one point in time, there's only one scale. If you want to make an example where you put all the link scales together in one kind of soup at the same moment in time, which is I think what a real fluid should look like, you are met with a restriction of how to fit, you can't, you have to fit them all together in such a way that they don't talk to each other and they don't interact. And the only way you can do that is by doing that.
So really to the hunt for non-atomic dissipation measures.
It's because the non-atomic is our way of trying to separate what we prove from what they prove. Right, I mean, there are different levels of cheating that are going on, right? Like, we're cheating because we're building a vector field that we didn't get this vector field from an experiment. We built the vector field so our proof would work. So we're cheating. We would like to reduce the cheating though. And somehow we feel that our example, which has all the link scales in it and really has to make some sort of renormalization group argument rigorous and does it like this is somehow less cheating than the cheating you do when you make the fluid sort of chop things up in time, which is really not what, I mean, I guess what we think is that if you ever analyze a real fluid and prove anomalous dissipation for a real fluid, you'll probably have to do some sort of argument that resembles our argument, we think, at some level. It'll have to be way more complicated and way smarter in many ways, but there'll have to be some component that I think roughly looks like this, or we think maybe. And this restriction that we're meeting here, I think is really there, yeah. Somehow if you didn't need that, then we think that Euler's solutions wouldn't need to be below 1/3 to make the anomaly, and we think that's not true. Yeah. I don't have a good answer, I guess. Yeah. Okay, so this example is good in some ways. It's good in the sense that as this parameter q, this artificial parameter q, which is slightly bigger than 1, as q goes to 1, and you look at all the scalings of our parameters in our problem, it matches what you expect of a real fluid in certain cases. Although we're debating about this eddy turnover time, but I bet it matches it in that case too, but we can talk about it. But for example, if you remember what Vlad has for the kappa m yesterday, the kappa m has some recursive definition, but it was of order epsilon m to the 1 plus alpha plus gamma. And you remember that gamma is this parameter that's of order q minus 1. So as q goes to 1, it's just 1 plus alpha. Alpha is going to 1/3 as q goes to 1. So this is epsilon m to the 4/3. So it says that the diffusivity at scale epsilon m is the 4/3 power of epsilon m. Okay? So that should be correct, right? That's the Richardson 4/3 law. And if you look at a lot of the other scalings coming out of this example, you'll see all the scalings that you would have in fluids. And so in some sense, in that sense, this is closer to being a fluid. It's obviously artificial though, because we built the scales in by hand. So what we'd really like to do is to somehow have a fluid, like a synthetic field, possibly, but we'd like to make B be a solution of maybe a stochastically forced fluid equation, where the stochastic forcing is something kind of canonical and reasonable. And then we would like to do the analysis on that. Okay, now that would have the disadvantage that it's random, and therefore I can't make homogenization estimates good enough to close the argument at all. I'm not even close. But it would be maybe more convincing to a mathematical physicist who wants to see sort of a more generic field. And so I want to next present results that we're working on now that do have results for sort of generic fields, but the fields are very far from having the exponents you would expect in a turbulent fluid. But it is related to models that physicists actually introduced in the 1980s. So I want to tell you a little bit about that with the last half an hour that I have. Okay? So we can go in the direction of more generic vector fields. Okay? Now, the vector fields that I'm going to write now are so rough that they're not even C alpha at all. In fact, they have some negative spatial regularity. What will be Holder continuous is the stream matrix. So they're quite far from being a real, a physical vector field. And because they're below, they're into the negative regularity, I don't have to worry about stuff like this. Because the problem with the reason that we had to do the sweeping is because the larger scales, the vector fields, the size of the modes on the larger scales, the amplitude, was larger than the smaller scales, right? Because that's a continuous function. A continuous function, the amplitudes on the smaller scales are smaller. And so I had to sweep them in order to make them all have some, effect, basically, on renormalizing the diffusivity. However, if you have the opposite situation where the smaller modes are bigger, then you don't have to worry about that. Okay? So I'm going to be in that situation, so I'm not going to have any need to do sweeping. And so I can just make my vector field actually not depend on time. Okay? So we're going to consider, I'll call it B. B of x, which does not depend on time. So it is stationary. Okay, so I don't want to say stationary because that means something else. So I'm going to say time independent. Okay, and I want it to be a Gaussian field. Okay, and I want it to be divergence free. Okay, and I want to study essentially the same problem that we study with LAD, but for a situation like this. And what I'm going to say is that the covariance, it's a Gaussian field, so I can describe its, what field it is by its covariances. And I'm going to just tell you how the covariances decay. And they decay like this: x minus y to some minus p. Okay, so there's some decay in the covariances. And let's see, what else do I want to say? There was some other, I want B to be isotropic. Is isotropic in law. Isotropic in law. Okay, so that means that there's no, if you look at B, you won't see it strongly pointing north-south and less east-west or something like that. Okay?
That's equivalent to the covariance being dependent only on the norm of x.
Yeah, I mean, this is kind of, okay. I really want this for x minus y large, and there's a constant here. But, yeah. I mean, you can take I want my B, in the way that I'm going to set it up in a second. Well, okay, anyway. My B is going to be rough, but I may do some sort of ultraviolet cutoff on some very small scale so that B is nice, and then I'm going to zoom out. Okay, so because I do an ultraviolet cutoff, this is not going to be true for x minus y less than 1, but okay. All right, so now I think I've used all my blackboard. No, I still have the blackboard here. Sorry. Okay, so physicist predictions. Physicist predictions. Okay, so the interesting case, by the way, is the case where P is less or equal than 2. Okay, because if P is bigger than 2, then somehow the correlations decay so fast that you find yourself in kind of only really having 2 scales in some sense. There's not enough large scales for anything interesting to happen, and you end up having it falls into the classical homogenization theory. Okay, so we're going to do the case p less than 2. Okay, and so these physicist predictions, let's see, so these let me try to give their names. So it's, I'm just worried I'm going to forget one of the authors, but it's Bouchot, Georges. Yeah, I am going to forget one of the authors. So it's this, Ledusal. So we found out about this paper because when one of the collaborators was giving a talk, Ledusal was in the audience and then wrote a long email with all the papers that should be cited, and he was actually right because we didn't know about this paper. I think there's a fourth author, but unfortunately I can't remember. This is 1987, so it's been quite some time. You're always about 40 years behind the physicists. So what do they predict? They predict that, and let me write the predictions in terms of solving the SPDE. Okay, so I'm going to write the predictions in terms of the stochastic flow. So there's no time dependence, so I just integrate this, and then I have, and let me just have Brownian motion of order 1. Instead of sending kappa to 0, I will just leave kappa fixed and talk about large times. It's equivalent, but it's nicer to talk about large times. So I'll put square root of 2 dWt. Okay, so I have a Brownian motion with variance 2 times t at time t. And I want to talk about this guy.
Are you any particular spatial dimension?
Yeah, so this works in any dimension d bigger than 2. Okay? What's important is that parameter p, not the spatial dimension. Yeah. So some people think about this problem and they say, I want B to be, I don't know, the grad perp of the Gaussian free field, and then in dimension D, and when you do that, that fixes a P. But it's the P that's important, not the D, if that makes sense.
The critical P2 is the same for all dimensions?
Yes. What P equal 2 means, and P equals 2 is critical, what P equals 2 means is that the stream matrix for the B is a log correlated field. Because it's really the stream matrix that should be important. So you want the stream matrix to have kind of positive Hurst exponent to be Holder continuous. And if it has Hurst exponent 0, then that's P is 2, and some logarithm happens. And then beyond that, something else should happen, okay? So the physicists describe what's going on in terms of this thing. Now they fix so now there's 2 sources of randomness, right? Because my field B is random, and then my stochastic process is random because of this dWt, so there's 2 randomnesses going on. So I want to first roll all the dice for the B and fix the B. So I'm going to kind of figure out what the B is doing, fix a realization, and then study the process. And the physicists make a point about this. They say that we want the results to be quenched as opposed to annealed. And this is what quenched means that this is frozen, okay? And you want the results to be almost surely in this B, okay? So we have this. Now what they say is that when P is 2, and I should say that the results they state are in terms of the scaling of the variance of this xt at time t. Okay, so we want to know what is the expectation of xt minus its mean. Sorry, there's 2 randomnesses, so I have to be careful. So let's say that the law of the B is given by this fonted P and E, so the math BB, P and E. And the law of the process is given by, I can't make it, it's supposed to be boldface P, and the P depends on the B and the starting point x naught for the process. Okay, and then you have a boldface E, B, and then x naught. Okay, so because I want the following result to be math BB, P, almost sure. So I'm going to put, the expectation that I'm going to put is the one for the B, and I'll start at 0. Okay. Okay, so this is another way of just writing the variance, starting at 0, having frozen the vector field B of this thing. Okay. That's what this is basically. Now what they say is when P is 2, this is going to be slightly super linear in T, which is saying that you have some super diffusion. And they say it should be a particular constant times T and then the square root of the logarithm of t. This is the critical case, so you assume that you expect some kind of logarithm. Okay? It's very hard to detect that in a simulation because square root of log t is, in practice, bounded by 10. So you can't really detect that. And then they say when p is bigger than 2, you have real power-like superdiffusion. So less than 2. Sorry, it's supposed to be strictly less than 2. You have that the same thing here should be proportional to t to a power 1 plus 1 over 4, 2 minus p. Okay? So this little bit of extra t is really superdiffusion. And you could rephrase this. In this case, if you write the problem like I do with Vlad, you will really have anomalous diffusion. I never know where the A goes and where the O goes. Anomaly, yeah, anomalous diffusion. So you'll have anomalous diffusion. In this case, you won't hear because there's some sort of weird ultraviolet cutoff that you have to do. You can't really make as much sense of it. But in this case, you'll have true anomalous diffusion. And you should have spontaneous stochasticity. So it should be that in this case, if you were to put a parameter in front of here and send the parameter to 0, that you still get a stochastic process in the limit. Like you get a limiting stochastic process. So here you should also have spontaneous stochasticity. Okay. So let me see. So how much time do I have to try to explain this? Now I need to find the eraser. Here. Okay. Quoi?
B is not even continuous.
B is not even continuous, yeah.
Very rough.
It's very rough, yeah. It's very rough. So B is not continuous, it's very rough. And that it means that when you look at because the physicists, how do they argue? They use a renormalization group argument. It's 3 pages. I can't follow a single line of it. But what's amazing is that when we didn't know about their paper, and what we do is we prove this one. And the constant we have here is explicit and it's deterministic. And the constant here in dimension d is something like 2 to the d for a particularly nice b that you fix. So there's you put the log Gaussian field with the right, the typical parameters. And this constant then you can compute explicitly. It's like 1 over pi to the d over 2, 2 to the d gamma function of d over 2, something like this. Okay? And then when he sent us the paper, he's like, you should quote my paper. In the email, we opened the paper and I was like, okay, what's in this paper? I can understand nothing. But then I find the same constant there. And I thought, they must have computed the same thing, no? So anyway, I thought that was fairly impressive. And then I was relieved because I thought my calculation was correct. I didn't drop a factor of 4 or something. So I was proud. Anyway, so they did in 3 pages what we do in much longer, but I think the argument must be the same. And what they say is that you should use a renormalization group argument, and the parameter that they follow is the diffusivity at scale, at the scale. And they get kind of a heuristic sort of ODE for the diffusivity at a particular scale. The proof at a high level is kind of like this one. You're studying the diffusivity at a particular scale. And I think the renormalization group argument is, they make a perturbation argument where they say, well, if you could ignore all these other things and just look at what the wiggles at that scale do, how does that change the diffusivity? Like, how does that change the increment? And then they derive in ODE for that. And so and they call this is called a beta function, I think. So their beta function that they derive is the same ODE that we derive in our proof, more or less, but using essentially the same heuristic, but it's just a longer proof. So, okay, so theorem. Okay, so this theorem we prove with Tuomo Kusi, who's my Finnish collaborator, and Ahmed Bourabi, who is a Courant postdoc. And we prove that in the case p equals 2, we have the physicists are correct. And moreover, we have a central limit theorem. So if you have a super diffusive process like this, then you should not have a deterministic limit in a sense, because the largest waves in your vector field, which are random, will affect the system at order 1. But if you have a logarithmic divergence like that, it means that the largest waves in your system, these sort of largest scales, affect your problem, but only they contribute O of 1. And so in relative terms, they're 1 divided by log t significant, and that can go to 0. Okay, so
The second name is Comte, maybe.
how do I spell it?
C-O-M-T-E-T.
Yes. Okay, so now it's out of alphabetical order. And then Georges and Bouchot wrote a book about that, right? And they have a very long book with everything in there, yeah. Okay, so you can find lots of stuff now. And they consider many more cases than I'm writing here. I mean, they have a whole book with many, many, many cases that they analyze. But, okay, so in the case p equals 2, the physicist's prediction is correct. And moreover, if you take the xt and you have to rescale it, so you have to look at it for a long time, and instead of looking at it for a long time, I'm going to put a parameter epsilon, which kind of makes the time zoom out. This would be the usual parabolic scaling, but now I have to divide by kind of a square root of log t in order to make it have a limit. So I'm going to put here a log t basically, and because this is a variance, I really need to divide by the 4th. So I do something like this. Maybe this should be absolute value. Okay, so if I divide by the 1/4 root of log epsilon in addition to the usual parabolic scaling that you would have for Brownian motion, that this will converge in law to a constant times the Brownian motion for some C star, and C star has a formula. Okay, and it's the C star that you would guess by looking at this constant here, the constants match, okay? So in some sense, we not only have the variance, but we have all the moments. Not only all the moments, but we have the full stochastic path described. It just becomes a Brownian motion, okay?
This is surprising because your equation is non-linear, so you expect to add a noise, since this is a flow map, it should be non-linear, so not Gaussian.
Yeah. So it's still Gaussian at this critical point. It's a little bit, I'm told that it's like, I don't know what I'm talking about here, okay? But if you look at the 5-4 model in QFT in dimension 4, it also has some logarithmic divergence, and it's also expected to have a Gaussian limit, even though it's critical. So it's kind of the same situation, I think. They prove that if there is a limit, it's Gaussian, but I think they haven't proved that the thing, okay. So I think that's Hugo, Duménil-Copin, and Eisenman, yeah. Okay, so what we're working on now, which we've proved, the paper's not finished. We've been working on it 1 year. I'm hoping that we'll finish it before the next year, is this case. So this case is pretty hard, because what happens is because you only have a square root of log t amount of superdiffusion, but you have an infinite number of scales that you need to analyze in order to see that. So it's kind of like the situation with Vlad. We have to homogenize an infinite number of scales. And these scales are not well separated like Vlad and I kind of did here with this super geometric scale separation. We can't cheat and make the vector field do what we want. It's given to us as this nice Gaussian field. And so we have to actually deal with that. And so our scale separation is like a factor of 10 or 3 or whatever. And we have to analyze it despite not having scale separation. And so our theorem, the mathematicians that were working on this thought that this result should be false. And they thought that you would only have this kind of scaling. They thought the physicists were wrong, and that you would only have this kind of scaling after you take the annealed expectation, so when you average over the vector field realizations. Because what they thought was happening was that, maybe I won't explain this for too long, but so this quenched result was considered surprising, and the analysis that you need to prove it is quite intricate. So we have to use homogenization arguments, but the arguments are not so simple like they are here in a sense. We really have to fight with the random homogenization problem. It's because we have a random field. Okay? What ends up happening, though, in this problem is that the diffusivity, so you prove this by showing that the diffusivity at scale r is the square root of log r. So the diffusivity is diverging as a function of the scale. Slowly, but it's diverging. And that divergence of the diffusivity tells you that the amount that the vector field is doing at any scale, which is of order 1, if p is equal to 2, that the amount that the vector field or the stream matrix is doing is relatively small. And because relative to the amount of diffusivity you have, it's small. So it's different from this situation, right? In this problem, for all of these equations, this was somehow bigger than this, which is reflected in the fact that this ellipticity contrast was diverging. So for Vlad and I, the vector field was always bigger than the diffusion matrix at each scale. In this problem, the vector field is becoming kind of small relative to the size of the effective diffusivity, and we're able to then get ourselves into a perturbative regime and then understand what's happening, which is kind of like what the renormalization group argument is, right? You want to enter a perturbative regime, and then you can compute it. So we managed to do that, and sort of surprise, in a sense, the mathematicians, but maybe not the physicists. Okay, so now the thing that we've been doing recently, so theorem, which is even more fun. So this is the same collaborators. And this is going to be in preparation for some time. So this is in preparation. Okay, is that we can do this case, but only perturbatively close to 2. Okay, so in the case p less than 2, but 2 minus p much, much less than 1. So we're able to make this explicit, how much you are less than 1, because everything is computable. But if you really tracked our constant to figure out how much less this, how small this had to be, it would be embarrassing. It's probably 10 to the power minus 400 or something. Okay, so it's still a mathematical sort of theorem, but it's away from, it's somehow in the supercritical regime. So in this case, the physicists are still correct. The exponent here is correct. So you can figure out this exponent because it's the only exponent that it could be from a very easy scaling argument. But now, see before this constant, and this was sort of deterministic. Here this is no longer deterministic, it's random. Because the largest wavelengths, which are random, contribute an O of 1 effect here. Okay, so you will not have convergence to a Gaussian limit. So what are we able to prove? We're able to prove that, okay, so if you had put, I'll just say that you have spontaneous stochasticity and anomalous diffusion. Moreover, one can prove anomalous diffusion, which is really the same thing. It's in some sense the same as the scaling here. It's just rescaled. But you can prove anomalous diffusion. We can prove uniform Holder estimates for the scalar, which is what right now is missing in this theory with Vlad, actually. for the scalar, and spontaneous stochasticity, so that the limiting process, you can define a limiting process which is going to be a random process and depends on the realization of the vector field. Okay? Now, I didn't think I'd like to say this, but it is true that the limiting process will somehow be supported on the weak solutions of this ODE. I think I'm forced to admit that that will be true. I don't know what this exactly means because the B is actually in a negative regularity space, but I think we can still make sense of that somehow. In some sort of, because when you have weak solutions, you can do stuff. But we will, anyway, show that there's a limiting process. This limiting process is very weird. For example, and I should say we can also prove intermittency. So we can prove, and we can actually talk about, we can actually say things about the what do you call this? The multifractal spectrum. So we have all kinds of things to write right now.
And the process is Markov.
Huh?
And the process is Markov.
Yes. Yeah. So we can talk about the multifractal spectrum of the solutions of the PDE that's associated, okay? Okay? So I think this result is interesting because I think there's not been a result, a rigorous, really rigorous result that's managed to prove all of this for a really random model with, with a generic vector field. Now that I understand how this is working, and that it's taken us throwing every bit of theory that we've invented in homogenization for the last 10 years, and I mean, this thing is, anyway, this is way harder than anything that I've ever done before, and the fact that we're able to prove this makes me very, very pessimistic that I'll ever be able to escape this perturbative setting. So in particular, what's happening here is that the vector field has regularity C minus 1 plus that, okay? So one way to visualize what's going on is that we just think about the regularity of the stream function. Okay, so here's the stream function's regularity, and here is 0. Here is 1. Now 1 is where the vector field becomes a function, and here is 4/3, which is physical, which is what we're doing with lead. Okay, I can do this, which is kind of weird and critical. That's the first theorem. And we can do this a little bit where this gap is actually not to scale. Okay, that gap is actually 10 to the minus 400 or something. And I am very pessimistic of going further this way, even for this simple model. I think it's very, very hard. I could imagine the kinds of things you would need to know to prove that, and it seems very hard. Okay? Now, once you go past 1, you're even in worse shape because you need to understand the sweeping. And we don't even know how to make a random model. Actually, maybe Laurent does. But we don't even know how to make a random model that has when we look at this vector field, we can decompose it into its scales and look at its random, it's going to be the sum of a bunch of random fields that live at every scale. Kind of like we were making with lead. Okay? But if you go past 1, then you need to incorporate the sweeping. And now you have to make a random field that somehow is like a solution of a fluid equation. And you have to show that it has all the scales that are active that are going to help you make the renormalization, make the enhancement of the diffusion. And I have no idea how to even make an example of a field that could do that. And again, my best case is the random field that you make that's supposed to simulate turbulence, right? And maybe that has the sweeping effect and we can show these scales, but I don't know. So Laurent has a way of building a random field. You start with a Gaussian multiplicative chaos and you add a lot of bells and whistles and you have a field that should look like turbulence. So the best thing that I can think of is maybe we try to prove it for that one. But even describing that field is quite involved. So I'm very pessimistic of going into here in the random case right now. I don't think we'll see this in my lifetime, but maybe ChatGPT will be able to find the proof.
The physicist prediction, nothing happens all the way after 0. I mean, it's all the same. It's
Well, the physicists, they can make an Taylor expansion around d equals 2, and then they can say plug in d equals 7, and they're happy with that typically, right? So we're able to like make the thing, you know, it's like we can show that the series converges in this range. For a physicist, they say, well, I mean, what else is going to happen? And they are happy with that, I think. But I really want to make a proof, and I don't know, you know, I think that the physicists are right. I think their intuition is solid, and I'm very frustrated. I mean, it offends me that I can't make a proof when they can make a prediction so easily. It's frustrating to me. So I'm trying to close the gap on what is predictable using these kind of heuristics and what is provable. And I'm not, yeah. Yeah. Oh, really? Good. I filled the time. I was worried I was not going to fill the time. Okay, so the last thing I wanted to say was to try to explain what is hard and what we would have to do in homogenization theory in order to, you know, first prove this and then in order to extend the range of parameters that we can understand. But I think in 5 minutes. So before I stop, I think we should thank the two organizers who gave us a wonderful conference. I'm sorry I'm not speaking in French, but they did a lot of work and they organized everything super well, and it's been a great week. No? What? In French. In French. Merci.